Hello everyone, today I'm going to present our work of safety by the SIGIR 2022, and the title is the MGPolicy Metagraph Enhanced Off-Policy Learning for Recommendations. And my name is Shang Wang and I'm from the University of Technology, Sydney. So in today's presentation, I will basically introduce our work through the following aspects. Firstly, the background, then the existing works and our motivations, followed by our methodology, the evaluation, and our conclusion of this work. Firstly, I want to introduce some major difference between the recommendation as reinforcement learning and the conventional recommendation. The conventional recommendation usually follows a statistic strategy by leveraging the organic user behavior log, such as the user item ID and item clicks, to predict future user preference on items. And on the contrary, the reinforcement learning-based recommendation follows dynamic user interactions. Taking this picture as an example, the recommendation system poses some specific actions to a user, such as a recommendation item, and in return, the users give the real-time user feedback, such as the click or not, to the recommendation system. So basically, the reinforcement learning-based recommendation aims to take the dynamic user feedback on actions to train the recommendation system for learning an optimal recommendation policy. So the advantage of the reinforcement learning-based recommendation is unique. Unlike some statistic method, for example, the matrix factorization, it can dynamically learn the recommendations based on user interactions with the agent and can also achieve the unbiased evaluation through the positive A/B test. However, the challenges of it is still severe. Because the data collection of the reinforcement learning requires the agent to interact online with the users. And in recommendation scenario, this online update of the recommendation policy is infeasible and expensive because post some untested actions to the users may terribly harm the user satisfaction with the system. And on the contrary, the off-policy learning aims to achieve the policy learning directly through the logged user feedback data. So without interactive access to the online environment, the off-policy learning can open a new direction to the reinforcement learning-based recommendation to abandon the expensive online training. So next, I will give a brief introduction to the off-policy learning as denoted in this figure. So in the first stage, the user feedback collection, the recommendation system poses some specific actions to the user, and in return, the user gives the real-time feedback to collect the state reward action pairs of the whole process, and such state reward action pairs are used to learn the target policy, and the target policy is finally used to deploy online to post actions to users such that the users' satisfaction can be finally maximized. And we denote the user feedback collection as the login policy here, and the policy that used to deploy online as the target policy. And in off-policy learning setting, the login policy and the target policy holds different distribution as denoted in this figure. As we can see from this figure that the login policy pi 0 occupies some login actions, while the target policy occupies some real actions that can never appear in the login actions as denoted in the pi 0. So the off-policy learning basically faces a severe challenge of the bias issue caused by the distribution drift between the target policy and the login policy. This is because that the log data can provide only partial information, while the reward for rare actions in the target policy are missing. And next, I will introduce some existing works on the bias correction topic and also our motivation. There are typically two types of works related to the bias correction in the off-policy learning, and the first type is the data imputation. It aims to train some logic models for correcting or padding values in the login dataset, such that the missing reward of the real actions can be padded by the trained logic model. So the data imputation method can naturally suffers from the inaccurate value prediction, And the second type is the inverse propensity score method. And the IPS-based method usually reweights each sample via the propensity scores, which is to assign low propensities to real actions to force the target policy not to visit these real actions. So basically, the IPS-based method can suffer from the poor gets poorer phenomenon, and in recommendation scenario, it can cause a typical question that an item will never be recommended simply because it never appears in the login policy. So in this work, instead of using the data imputation of the IPS-based reweighting method, we claim that rich context information in metagraphs is useful for inferring the missing rewards of the real actions. And here we take a vivid toy example to illustrate why the context information in metagraphs can be useful in such scenario. And suppose we have a user U1 here that interact with item 1, 2, 3, and since user U1 give a positive feedback to the item I2 and item I3, which has the attribute of the attribute of A1 and the T1, so we can infer that the user can potentially give positive feedback to the item I4, which has the same attributes A1 and the T1 with the item I2 and I3, and also the since the user 1 give the negative feedback to the item I1 that has the item attributes of the T1 and A2, so the item I5 can potentially receive the negative feedback from the user here. So having noticed the importance of the context information in metagraphs, in this work we aim to investigate firstly how to correct the off-policy bias with the assistance of the metagraphs, and secondly we want to propose a novel end-to-end off-policy learning framework that can incorporate such context information, meanwhile achieve the unbiased evaluation. Next, I will introduce our methodology in this work. And basically, our methodology contains 4 main components. The first one is the metagraph attention network that learns the context information from the metagraphs. And the second component is the state representation learning that incorporates context information into the current states. And the next component is the neighbor attentive candidate selection that filters out irrelevant items to improve the sample efficiency. And the final component is our developed unbiased off-policy learning module that develops counterfactual risk minimization learning objective to achieve the unbiased policy learning. The first metagraph attention network is based on the transformer architecture. It parameterizes the identities among the metagraphs as the vector representations. Here, specifically, we design 3 operators, the attention operator, the message passing operator, and the aggregate operator to draw the final vector representations of the context entities. And the second component is the context-aware state representation learning module, which is a GRU-based unit. And it aggregates the context-aware action representations into the user states by passing different GRU units. And the third component is the neighbor attentive candidate selection module based on the attention mechanism. And in this component, we filters out irrelevant items to improve the sample efficiency of the action search, as denoted in these 2 equations. That firstly, we learn the attention scores based on the current user state, and then the overall attention score is based on calculation the software max among all the attention scores on item entities. And finally, we can draw the final candidate action set by using both the structural information in the metagraphs and also the attention scores learned by the first 2 components. And the next module is our unbiased off-policy learning module, which is the counterfactual risk minimization-based learning module. Firstly, we design a 2-stage topical recommendation policy by passing the learned user state through our GRU unit and also the action set by our candidate selection stage. And then we incorporate the IPS estimator by balancing the top K recommendation policy and also the login policy distribution. And finally, by plugging the IPS estimator to the top K recommendation policy, we have our final counterfactual risk minimization on the recommendation policy, which draws from the policy gradient denoted in the last equation here. So next, I will give the experimental evaluation of our proposed method. So in the evaluation part, as we focus on the recommendation performance of our MG policy, so in this presentation, we only present the recommendation performance of our model via some state-of-the-art recommendation models. And the final recommendation performance comparison between the SODA model and our MG policy is denoted in the table here. We can find that our proposed MG policy consistently yields the best recommendation performance among all datasets on both of the evaluation metrics. And the second finding is that our MG policy can achieve remarkable improvement on extreme sparse Douban book dataset with a density of 0.27 density, and compare with it on the movie lens dataset with the density of the 4.26 percentage. And we also include some ablation study and case study in our original manuscript. So if you are interested in our performance of the proposed model, please go to refer our accepted paper in the SIGIR 2022. So in conclusion, in this work, our contribution is that, firstly, we are the first to leverage the contextual information in metagraphs to provide the target policy learning to correct the bias in the off-policy recommendation learning. And secondly, our MG policy is designed with the efficient two-stage off-policy gradient method. And lastly, based on the context-aware state representations, we include a counterfactual risk minimization to achieve an unbiased policy that can maximize the long-run reward for the recommendation. So this is pretty much my presentation today, and thanks for listening. And any comments or questions?